All right, welcome to AP Physics C. As I mentioned at the end of the last video, two left, right? So you got the LC circuits and the Maxwell's equations, okay? So this is the last of our circuits. There is one more circuit that you can learn about, but AP Physics doesn't really go into that circuit, and that's an RLC circuit. So you put all of them together into one giant circuit. The only thing I'm missing in my little diagram here is there would be a power source, right? A battery in the circuit with a switch, right? So you can charge versus discharge, close open the switch. So an LC circuit is a circuit that contains a charged capacitor and an inductor with little resistance, okay? Little to no resistance is what you really want. If it is a fully loaded capacitor is connected to an inductor, it will discharge, right? Because remember, that's what capacitors do. They store the charge to discharge it. Okay, and it'll discharge through the inductor. So what happens is when the capacitor runs out of charge, then the inductor will produce an induced current, right? So we talk about all this stuff with inductance and inducing currents to stop the current from decreasing, right? So it says, no, I don't want you to decrease. So what I'm going to do is I'm going to send charge back to you so that you can recharge, you can build your charge back up, and then you can continue the process, right? And so exactly what happens is they're basically passing this charge back and forth. So what we say is that the LC circuit will repeat and it oscillates, right? And in the mechanics course, we learned about oscillations through pendulums, right? And mass spring systems. So what will we be able to calculate? Well, pendulums, remember we did 2 pi square root of L over G. And then with mass spring systems.
Part of this interruption equals Student Council is hosting a toy drive for children who might not receive a Christmas.
Sorry about the announcements, but welcome to life.
Donate a toy or two to G208 for 3 hours of community service in return. More details are on our Instagram at RHS_Stuco2K24. There are flyers around the school as well for you to check out. The deadline for the toy drive
just waiting
is
for the
this
announcement
Friday.
to stop.
Thank you guys. Have a good rest of your week, Eagles.
All right. So if you go to RHS, donate toys. All right. Apologize for the interruption, but welcome to life, right? I'm not going to edit it out because it's very funny to watch students react to that. All right. So the period of oscillation for this, because it's going to go back and forth, back and forth, back and forth, back and forth. So it's going to oscillate back and forth. Can be found using a differential equation. Again, I'm not going to show you that because I would make this video from like maybe 9 minutes to 20 minutes, but I'll give it to you. So T equals 2 pi root RC. Oh, not RC. Sorry. We're not resistor capacitor circuits. We're LC circuits. Right? So T equals 2 pi root LC. But also remember, you may be asking to find a frequency, which is 1 over T, which means you can rewrite this equation to be 1 over 2 pi root LC. Oh, sorry about that. I didn't mean to blank the screen. All right. So you can either find the period first, then substitute into F equals 1 over T, or you can just find the period and frequency separately. But that's how you calculate the period of oscillation. And then a lot of times what will be asked is like, what is the energy stored? Because you have a capacitor and an inductor, they will just simply store their energies. So Q squared over 2C for our capacitor, and then 1/2 Li squared for our inductor. But something to note, when energy is max in a capacitor, the energy in the inductor is 0 and vice versa. So when the energy is max in the inductor, the capacitor has 0 energy. Okay, so that allows you at times to say, okay, if I'm just looking for what is the maximum energy in a capacitor, I can cross out then anything to do with the inductor because now I know it's equal to that E value, okay? And also remember, capacitance is Q over V, because you may have to find charge, just saying. So let's look at an example problem. So a capacitor with a capacitance of 47 microfarads is charged with a 12-volt source. At the time t equals 0, the capacitor is discharged through the inductance of 870 nanohenries. A, determine the period and frequency of the LC circuit. B, determine the maximum energy stored by the capacitor. And C, determine the maximum current through the inductor. All right, so part A, very simple. T equals 2 pi root LC. Now, remember, microfarads, nanohenries. You need to convert those. So 2 pi root, now micro times 10 to the negative 6th, nano times 10 to the 9th, times 10 to the negative 9th, right? Do 2 pi, square root of that, and you find that it's going to be very fast, because it is a value of 4.02 times 10 to the negative 5th second. So what does that mean? It oscillates back and forth every 0.4 microseconds, okay, or 402 milliseconds. Okay, so it's going to be pretty fast. Now, find the frequency. Well, you can do that 1 over 2 pi root L over C, or you can just simply do 1 over T, which is kind of the shortcut, lazy way, right? And so we get a frequency of 2.5 times 10 to the 4th hertz. Okay, if you forget what hertz are like our radio stations, right? It's the amount of cycles per second. So it goes back and forth 2.5 times 10 to the 4th cycles. Like it goes back and forth every second. And so that's why you get such a small value for the second, because it's doing all that, right, in 1 second. All right, the next part, determine the maximum energy stored by the capacitor. So the first thing you're going to need to do is find how much charge is on the capacitor. You're going to do Q equals CV. So you're going to do 47 times 10 to the negative 6th times 12, which says that there are, there it is. I almost didn't write down the number. 5.64 times 10 to the negative 4th coulombs. And so if we're looking for the maximum energy in the capacitor, that means there's no energy in the inductor. So we're going to say 1/2 Q, equation slipped my mind, double check, Q squared over C. So 1/2 times the number we just calculated, 5.64 times 10 to the negative 4th, squared over capacitance, which was 47 times 10 to the negative 6th. Okay, let me make sure I did square that. So 0.5 times 5.64 e to the negative 4th squared divided by 47 e to the negative 6th. I did. So the maximum energy, you know what? Let's write in scientific notation. Because the calculator does not spit it out in scientific notation, but we can write it in scientific notation. 3.4 times 10 to the negative 3 joules, or you can say 3.4 millijoules. Okay, so now this is the total energy of the system. So for part C, it says, what is the maximum current through the inductor? So if we're looking for maximum through the inductor, that it's minimum through the capacitor. So we use the 1/2 Li squared equation. Okay, and we solve this for I, which would be root 2e over L. So we do square root of 2 times 3.4 times 10 to the negative 3rd over 870 times 10 to the negative 9th. Okay, so 2e 3.4, 2 times 3.4 e to the negative 3 divided by 870 e to the negative 9th. There's going to be a big number. Take the square root of that. And we get a current of 88 amps. Right, so that's the current that is flowing through the inductor, right, over when the energy is a maximum. And what happens is that current shifts based on, where it is in its process, right? So where does it go, okay? All right, so we're down to our last video. The great thing about the last video is we don't do any calculations because We've already seen all these equations before. The thing is, they're Maxwell's equations. They are a set of special equations that James Clerk Maxwell combined together to describe this electromagnetic phenomenon. So I'll see you there.